Hi, welcome to another practical session where we are learning spatial statistics and spatial econometrics using R. I'm Saif and this is session 5 and today's topic is computing variograms, computing experimental variograms, part 2. Last time we did part 1 and I hope that you all watched that, because if you didn't watch that, then maybe today things will not really make sense. I won't do this whole spiel again. If you've been watching the videos, you've probably heard me say it many times. We're focusing in these sessions on gaining programming skills needed to perform spatial statistics and spatial econometric operations in R. But programming skills are founded on clear conceptual understanding. And programming skills and understanding are involved in a kind of circular relationship that if you clearly understand the theory, then it should be easy for you to program. And the more you program, the more you work, you try things on your own, the more mistakes you make, and the more number of times you fix them and go back to trying again, the more you play with the code and think about the results that you're seeing, that should hopefully clarify your conceptual understanding of the subject. This is actually one of the best ways to learn the subject, is by applying it to real world problems. And I hope that at this stage in the course, some of you are actually starting to notice that. If you're not noticing that your understanding and your skill acquisition are feeding off of each other, then maybe you can review or reassess where it is that you need to spend more time. So last time we estimated a variogram. We talked about stationarity. We also talked about how to remove trends, and if there is a spatial trend in the data, what that means, and how to remove it. This time we'll go further in estimating variograms. But when we do that, what you should be familiar with, which I will not necessarily really explain, is the idea of anisotropy. The idea that spatial variation is not necessarily similar in all directions. It's not isotropic. The things vary spatially in one direction in a different way, and in another direction in another way. And this is something that we will point out in the data, but I'm not going to go into it conceptually, so this is something you should already know. And also the idea of binning, that you have a continuous range of values and then you bin them into some discrete intervals. This is something that we will use, so this is something you should already be familiar with. Skill-wise, you should have already estimated an omnidirectional variogram. So an omnidirectional variogram is where direction plays no role. It's the same in all directions. We're saying that the spatial variation in the data is the same in all directions, which is rarely ever true. But that is what we did in the prior video, because it's simpler, and this is something that you should know how to do, because we're going to build on top of this. Of course, you know the Muse data set already. And so what will we do this time? We will add the idea of direction or anisotropy to our variogram estimation. And we will play with cutoff and width parameters. So we will not do this. So estimate a variogram using a new data set. This is something that we will not do. So that's scratch that. We will do that in the future. Okay, so this is a term that you might come across if you read material about geostatistics, or if you read papers. There's something called the direction of maximum continuity. And that's a big term, but what I want you to do is to understand this more, and to also appreciate that spatial variation differs by direction. That, in certain directions things vary a certain way, and in another direction maybe not so much. So this is the data set that we've been looking at. This is zinc concentrations in parts per million over the river bed of the river Muse. Now I want you to look at this plot and tell me which is the direction in which the values are most similar. or what is called the direction of maximum continuity of values, or conversely, the direction of least variation, in which the variation is the least. So you can look at these sort of cardinal directions. 0, which means north. In the GStat package, 0 means north, which is what I've said here. This is from the GStat literature, which you can click on this tutorial here and go to. It's on page 13. So 0 is north, 90 is east, 45 is northeast, and 135 is southeast. And of course, 0 is north, but also south. I mean, it's the north-south direction, right? It's this direction. So 0 to 135, you kind of cover everything, right? Because everything else, like 90 is both 90 and 360, et cetera, right? So all you need is 0 to 135 to cover the whole, sort of the whole range. So let's see, let's begin with 0. So if you move in this direction, you encounter some circles, right? So they are of a certain size, and then smaller in here, kind of medium size, then large here, and then again large. So there isn't a lot of continuity. I mean, the circles seem to vary in size in this direction. Similarly with 90, again, like larger circles here. And when I say 90, I mean if you draw parallel lines, like 90 direction over the whole domain, not just this line. So if you just move in this direction from left to right, like large circles and then followed by smaller, smaller, smaller. So even in the 90-degree direction, there seems to be some variation. Well, how about 45? So if you move in this direction, so if you start here, and let's see, we start moving this way, so we kind of encounter circles, all of which are kind of large. And then if we start here and then move this way, then all of the circles in this line are kind of similar in size. So it seems that in the 45-degree direction, there is the most amount of continuity. That's a vague sort of term, but visually at least, there is the most continuous values are encountered in this direction. And because spatial trends are not good, and we like to have small variations in values when we are estimating variograms, often variograms are estimated along the direction of maximum continuity. And there's a large discussion around this. This is not, again, there's no hard and fast rule for why that you have to do this, but this is often done. It's a kind of heuristic approach in research. And then, so when we estimate a variogram in this direction, in the 45-degree direction, which is what we will learn how to do today, what it does is it actually considers all point pairs within a sort of conical or triangular region around the 45 direction. So these two arrows, all of these point pairs that are in the ambit of these two arrows will be considered. So it only considers variation in a certain direction when calculating the variogram cloud. So remember, when it calculates the variogram cloud, it takes pairs of points. So in an omnidirectional variogram, it will take pairs of points in every direction, whereas in a directional variogram, it will take pairs of points only along this direction lying within this conical or triangular region. So it will look for variation selectively and not omnidirectionally. I hope that's clear. And if it's not, maybe you should review the video or pause it here and think about it for a while, because now we're going to go to our coding session with R. So before we do that, it would be nice to just have this firmly planted in your mind. Okay, so let's move to the code. Loading libraries, easy. And then make our spatial data set using the data from Muse. I'm going to clear all of these windows just so that we're working from scratch. Let's not have anything. So let's load our libraries. Then make our spatial data set. So I get an error. See, this is why it's important to. So it says could not find function make spatial data. So the reason it couldn't find the function is because I had cleared my environment. And when you clear your environment, everything that was previously loaded is lost. So I need to go and actually reload this function. So remember, this function was defined last time. So it will be available in the file that we used last time, the file corresponding to session 4. And I have to source this file. And when I source this file, I get this function back, make spatial data frame, right? Make spatial data muse, right? So now I can go ahead and make this data, call this function, and then this time it's fun. Oh, let me get rid of this, sorry. So let's make our spatial data. And then now look at this line of code, the one that I just ran. So this is the variogram function. You know this already. This is log of zinc, assuming a constant mean. So typically, if we do directional variograms, then we assume constant mean. If you do a directional variogram plus a trend removal, then the results, like you have to think carefully about the results because it's not obvious as to what that really means. So we will assume constant mean because see, now we are estimating along the 45-degree direction where the variation is very little. So the constant mean assumption is actually not so outlandish. And then we will provide our data. And then we provide this additional argument called alpha, and alpha is the angle. Alpha is this angle. This angle right here is alpha. So 45, 0. So 0 to 45 is 45, and then 0 to 90, and 0 to, so we want 4 values for the angle, 0, 45, 90, and 135. And that's what we mean by alpha. So we give these values here, 0, 45, 90, 135. Those are the directions in which we want it to estimate the variogram. And once it does that, we would like to plot the variogram. So now, as is expected, instead of 1 plot, we get 4 plots. And each of these corresponds to a directional variogram in a particular direction. So let's read this plot here. This bottom right plot is the variogram that corresponds to the north, the 0 direction, then 45, and then 90 up here, and then 135, right? So let's zoom this out so you can see a little better. So this is the north-south direction. This is 45 degrees. This is 90, which is east-west. This is 135, right? So one thing that we should notice right away is that the variance, the value of semivariant, which is gamma h on the y-axis, is the least for the 45-degree direction. It's the like this variogram is kind of the most gentle, shallowest, and also the lowest. Like the actual y values are lower than all the other 3. And that's to be expected because we just saw in the data that the 45-degree direction is the direction in which the variation in the data is the least. If you move in this direction, you basically encounter very similar values. And that's why we see the least variation in this variogram. Now that may or may not be a good thing depending on what you're trying to do, but we should be able to correlate this with the data. Now there are some additional parameters that we can pass to a variogram function. And these 2 parameters are called cutoff and width. And these it's important that we be familiar with these parameters because you often need to provide correct values for these in order to get sort of a reasonable result. And cutoff is basically the maximum distance within which we want to consider point pairs. So think about this. You have this data, right? Now, when we compute a directional variogram or a non-omnidirectional variogram, it takes pairs of points, so these 2 points, these two, so every single pair of points, and computes the semivariance between those 2 points, the values at those 2 points. But there may not be a situation where we want to consider points maybe that are here and all the way here. Like maybe there is some cutoff beyond which we don't want to consider point pairs. So if we are looking at this point, then maybe we only want to go to this distance, and beyond that we don't want to pair anything with this point because we don't believe that there is any relationship between points that are that far away. So for example, if we know that zinc concentrations in a riverbed are really only correlated within a distance of, let's say, 50 meters, then and we know that, where the river starts somewhere in the mountains and ends somewhere in the plains, then zinc concentrations out in the mountains don't necessarily reflect any relationship with the zinc concentration where the river ends in the delta. So we only want some local correlation, so we should provide some cutoff distance. So it will not consider point pairs beyond that distance. And the cutoff value that I've given here is 1,000. I just looked at this graph. It goes from 0 to 1,500, but I'm saying that beyond the 1,000 point, I don't want to consider the variation. And then the width is the distance, the size of the bin. So so if I say 100, then basically all point pairs that are within 0 to 100 units of distance apart will be considered one bin, and it will plot 1 point for that whole bin, right? So if we believe that there is a lot of small scale variation, so essentially the width is the distance between 2 consecutive points in a variogram. So like this distance in the x direction between 2 consecutive points, any 2 points is the width of the variogram. So what does this mean? Like should we have a large value, or these are all semi-artistic decisions because this will depend on you. There is no right or wrong answer, but it should correspond with what you know about the data generating process. So if you think that there is a lot of variation at small distances, then you need to have a smaller width to capture that variation. But if there isn't a lot of variation at small distances and you use a small width, then you will capture a lot of noise. But if you use a width that's very large, then you will smooth over a lot of localized variation, which is informative and useful. So this is also something that you have to try and sort of play with and see at what value you get results that you consider reasonable. So I've used a width of 100 here. So let's run this and then plot the variogram. So you can see that the distance between the points increases, fewer points, because I'm binning a lot of points together into one. So in the variogram cloud, any point pairs that are between 0 to 100 units of distance apart will be averaged to one value. Let's try a width of 50 and then plot the and let's plot the variogram again. So you see now the distance between points decreases. So there's more points now. So we're capturing finer scale variations. And also know that these are not exact. So when you do a width of 50, if I look at this, so my object is called logzinc.variogram.directional, so lzn.vgm.dir. So let me open that up and see what a variogram object actually looks like. The first column is called NP, which stands for number of points. That means the number of points that belong to that particular bin, right? And then so wait, let me show you, before I do this, let me show you a variogram cloud, right? then it will become much more clear. So let's see the cloud. Let's plot this cloud. Yeah, so this is the cloud, right? And this goes from 0 to some value just over 1500, and this is the values for every single point pair. So in order to go from this variogram cloud to the variogram, I need to group these points together. So essentially I need to decide what will be the size of my bin. So if my bin is 0 to 100, then I will go from 0 to about 100 and then group all of the points that are separated between 0 to 100 units of distance apart, and then 100 to a 200, 200 to 300, 400, 500, right? So it's basically how I am averaging or how I'm grouping these points in the cloud to go from the cloud. If this is the cloud, then what is the, let me show you then the variogram to this variogram. So it groups the points and averages them, because the variogram is actually the expected value of those of all of the points in a particular bin, and you get this variogram. So if I had a smaller value for width, you would see many points between these 2 points as well. But this is not exact. So for example, I did a variogram here in which the width was 50. Sorry about that. The width was 50, right? And then if I go here, it actually tells me the distance, the value of h for every bin. So 0 to 82.7 or so is in one bin, then 82 to 132 is another bin, 132 to 178. So these values are actually not equal. They're not equal. They're roughly equal. So when you say a width of 50, it's not going to give you a width of exactly 50. So I did a width of 50 here, and if I subtract the value of the distance for the second bin minus the first bin, then I don't necessarily get a value of 50, I get 49.57. So that's close, but not exact. Similarly, if I do a width of 200, then like the distance, the sort of the difference between the first and the second bin is 164, 197 between third and second, and then 197 between fifth and fourth. So it's not exactly 200. So this is just to show you that when you provide a value for width, it doesn't always give you points that are exactly that distance apart, but roughly that distance apart. And then I plotted here the variogram when the width is 200. So you see now you have very, very few points. So this is typically, I think for this particular variogram, I'm pretty sure that this width is too broad. We're smoothing over, we're losing a lot of local variation. And if you lose local variation, then your variogram estimation can actually be typically wrong. So what is the right width and the right cutoff? This is something that you will have to consider carefully depending on what your research question is. So that's all I had for that. So what did we do today? We estimated anisotropic variograms, something that can be very, very useful. And anisotropy is a property of most spatial processes. There are very few spatial processes that are truly omnidirectional or isotropic or the same in every direction. And we also considered the effect of cutoff and width parameters on the final estimated result. This is just the beginning of geostatistical modeling with the GStat package. If you want more, please go and read the latest manual. I don't have the scope nor the time to go into everything right now. My goal is just to get you started. But definitely check out the manual, the latest manual, for a lot more ideas on what you can do. That's it for now. Thank you very much for your attention.